Good morning, everybody. Hope you're all healthy and safe at home. We shall move on to the next section of our third module, section 9.16, Divergence Theorem. So in this section we shall be discussing about the theorem which is called as the divergence theorem and how we can apply it to evaluate the double integral. Q of xyj be a vector field, okay, and consider the unit normal on the curve C. Okay, on this curve C, consider the unit normal to be n is equal to dy by dsi plus dx by dsj. Then what will be f dot n? F dot n will be f dot n into ds will be nothing but integral of what? It will be integral of dou p by p into dy p into dy plus q into dx. Okay, so that is actually nothing but it is similar to the divergence thing. So we can express this integral over C f dot n ds in terms of a double integral of divergence of f with the help of Green's theorem. Okay, so this is how we are going to introduce the concept of divergence theorem. Actually, this has come as an extension of the divergence theorem. So it's just integral over C f dot n ds can be expressed as the double integral of divergence of f. Okay, that can be proved with the help of Green's theorem. So this comes as this statement can be expressed, or it can be considered as a special case of the divergence theorem. So let's see what is divergence theorem. The statement is as follows. Let D be a closed and bounded region in the 3 space with a piecewise smooth boundary S that is oriented outward. Let F be the corresponding vector field in which P, Q and R are all continuous and have continuous partial derivatives, first partial derivatives, because then only we can express the divergence, right? So this is an important factor. It should have they should be continuous and they should have continuous first partial derivatives in a region of 3 space containing D. Then double integral over S f dot n ds is nothing but triple integral over D divergence of f dv. Okay, so this is the statement of divergence theorem, that is double integral over S f dot n ds is nothing but triple integral over D divergence of f into D into V. Okay, so the earlier statement, the statement that we made in the previous slide, comes as a consequence of this particular theorem. So we had seen how we can evaluate integral over S f dot n ds with the help of the curl function, right? So here we are using the same, we are evaluating the double integral with the help of the divergence of that particular vector field. So we shall see the examples which are given in your textbook. One is how to verify that divergence theorem. So first example 1, let D be the region bounded by the hemisphere x square plus y square plus z minus 1 whole square equal to 9, where z varies from 1 to 4. Okay, and the plane z equal to 1. So what is our region? Region has a hemisphere and it is the region is bounded between the hemisphere and the plane z equal to 1. So you can see the blue colored, blue shaded region, blue shaded portion is our region D. This is the part of the hemisphere and it is bounded by the plane z equal to 1. We are asked to verify the divergence theorem for the function vector field f is equal to xi plus yj plus z minus 1k. Okay, so first let us I hope the figure is clear. This is our region and the cream colored portion is actually the projection of this region onto the xy plane. Okay, so what will be we have to verify double integral over S f dot n ds is same as triple integral over D divergence of f into dv, right? So let's see first of all let's see the right hand side part, that is triple integral over D divergence of f into dv. Now what will be divergence of f? It is dou p by dou x plus dou p by dou y plus dou p by dou r by dou z. Sorry. So dou p by dou x is 1 plus 1 plus 1, that is 3. So divergence of f is 3. So this triple integral is nothing but triple integral over d, 3 into dv. That is nothing but 3 is constant, triple integral into dv. So that is, this integral is nothing but the volume of the hemisphere, right? And the volume of the hemisphere is given by 2 by 3 pi into r cube, radius. Here the hemisphere is having a radius 3. Okay, so the volume of the hemisphere is 2 by 3 pi r cube, that is 2 by 3 into pi into 3 cube, that is nothing but we will have the value to be 3 into the volume, that is 54 pi. Okay, so this is our one side, that is the right hand side is 54 pi. Now we have to check whether that is equal to double integral over s f dot n ds, right? Now here we have divided this region into two surfaces. One is S1, that is the surface of the sphere, hemisphere, and S2 is this particular plane z equal to 1. Okay, one surface S1 is the hemisphere and S2 is z equal to 1. So first let us consider S1 and evaluate double integral f dot n ds. Okay, so for that we have to evaluate what is n, that is the unit normal, right? So here the surface is given by g of x y z is equal to x square plus y square plus z minus 1 whole square. This is what we usually do. So g is given to us. If g is given to us, then we can easily evaluate what is the unit normal. N will be del g divided by norm of del g, right? That is x plus y, xi plus yj plus z minus 1k divided by root of x square plus y square plus z minus 1 whole square. So this value comes out to be x by 3. That is, this is equal to, we know this is equal to 9, right? X square plus y square plus z minus 1 whole square is nothing but 9. So root of 9 is 3. So we'll get x by 3i plus y by 3j plus z minus 1 by 3k. So we know what is n. Now we'll determine what is f dot n. So f dot n will be nothing but, f is the same thing itself. So f dot n will be x square by 3 plus y square by 3 plus z minus 1 whole square by 3. Okay, so we can simplify it and you will get it as 1 by 3 into x square plus y square plus z minus 1 whole square, which is 1 by 3 into 9, which is given to us. So that is 3. So f dot n is again 3. And what will be ds? ds will be, by the formula, it will be 3 divided by root of 9 minus x square minus y square into dA. Okay, so double integral over s1 f dot n ds is nothing but double integral over r 3 into 3 divided by root of 9 minus x square minus y square into dA. So once we have x square and y square, we should move on to the polar coordinates, because that will be much more easier. So here region is our circle, so the radius r will be nothing but varying from 0 to 3. It is a circle of radius 3. R varies from 0 to 3, and the theta will be the whole circle, so 0 to 2. So this integral will be nothing but integral 9 into, because 3 into 3 is 9, 9 into integral 0 to 2 pi integral 0 to 3, 9 minus, this is r, right? 9 minus r square whole raised to minus 1 by 2. dA will be changed to r into dr into d theta. So evaluating this will not be much of a problem here. We'll have to put the substitution method and solve it. It is easy only. So solving this, we get the answer to be 54 pi. So the triple integral was also 54 pi. So this integral over S1 is also 54 pi. So this means that the integral over S2 must be 0. Right. So let's see whether it is 0 or not. Now if you consider S2, S2 is given by this plane Z equal to 1. So the outward normal will be facing downwards. Right. So here in this case, N will be nothing but N equal to minus k. Okay, so if n is minus k, then what will be f dot n? The dot product would be minus of z plus 1, because our f was given out to be xi plus yj plus z minus 1k. So into f dot k n will be nothing but minus of z minus 1. So that is minus z plus 1. So now let us evaluate integral over S2 into f dot n is minus z plus 1. into ds. Okay, but here the surface S2 is nothing but z is equal to 1, right? So if we substitute this z is equal to 1, this term will be 0. So this integral is 0. That's why integral over S2 becomes, or it turns out to be, 0. So this is how we can verify the divergence theorem. First we shall evaluate the triple integral into divergence of V, divergence of F, and we have to evaluate the surface integral. So in this case we divided our region into two surfaces, one consisting of the hemisphere and the other the plane z equal to 1. Now this is another simple example which we can easily see, that is we are given a vector field f is equal to xy into I plus y square zj plus z cube k. We are asked to evaluate double integral over s f dot n ds. Okay, where s is the unit cube, it is given by everything varies from x, y and z lies between 0 and 1. So here we have to evaluate double integral over s f dot n ds. So how can we easily do it? We can just evaluate it with the help of the divergence theorem, because double integral over s f dot n ds is nothing but triple integral over the d region into divergence of f into dv, right? So here what will be divergence of f? Divergence of f is del dot f, that is nothing but this is p is xy, q is y square z, and r is z cube. So it will be dou p by dou x, that is y plus 2yz plus 3z square. So that will be our divergence. So the formula, this double integral over s f dot n ds will be triple integral over d y plus 2yz plus 3z square into dv. So here since our variation of x, y and z everything is directly given to us, it will be useful, or it will be simple if we just evaluate it just like that. So we don't have to convert it into any polar cylindrical coordinates or spherical coordinates and all. So this is everything varies from 0 to 1, 0 to 1, 0 to 1, y plus 2yz plus 3z square into dx into dy into dz. So what will be the value? With respect to x, we have to evaluate it. We can solve this by simple integration. So solving, we will get the value to be 2. You can just verify it. There is nothing much complicated in this evaluation. So you can get the answer to be 2. So that is about our divergence theorem and how we can apply it, or how we can use it to solve the problems. So one type of problem is verifying the divergence theorem, and the other type will be like to evaluate the double integral over s f dot n ds. So that can be easily done with the help of the divergence theorem. So I'm not discussing further anything about this section. This is the main thing that we have to concentrate on, that is how to use divergence theorem to evaluate the double integral. So that's it. Thank you. Stay home and stay safe.